reversible and irreversible cells. Reversible and irreversible cells. So let's see what about reversible and irreversible cells. The first one, that is reversible cells. So what are reversible cells? So here the best example for the reversible cell is Daniell cell. Daniell cell and the secondary batteries. That means rechargeable batteries. So that come under the reversible cells. So in these two examples, the Daniell cell is a very good example for the reversible cell. So the Daniell cell's EMF is electromotive force is 1.1 volts. So it is represented as zinc sulfate and copper sulfate. Copper. Yes, we know that the cell representation of the Daniell cell, it is just like this one. Now, when we call the reversible cell, now here a cell which obey the following three conditions of the thermodynamic reversibility is called reversible cells. So there are some thermodynamic conditions. If these obey these three thermodynamic reversibility conditions, then only we can call as it is a reversible cells. So let's see what are these thermodynamic conditions. So here the first one is, if the Daniell cell is connected to an external source of a EMF equal to its that is 1.1 volts, then there is a no current flow and also there is no chemical reactions takes place in these cells. So that is the first condition. The external EMF is also equal to when it is also equal to 1.1 volts, then there is a no current flows. There is a no talking about the current flow and then there is a no chemical reactions takes place. So that is the first reactions, first condition. And the next condition. So if the external, see this one, if the external EMF is made slightly less than 1.1 volts, slightly less than 1.1 volts, then a small amount of current flow. See here, when you made the external EMF is made slightly less than 1.1 volts, so then a small amount of current flows from the cell, and also a small chemical reactions occur in the cell. So this is a second condition. So the third condition, coming to the third condition. So here it is, if the external EMF is made slightly, if you give the external EMF, it is made slightly greater than 1.1 volts. Here also the current will flow in the opposite direction. See here, if the external force it is greater than the 1.1 volts, that means it is greater than the EMF of the Daniell cell, then the current will be flow in the opposite direction. See this, in the opposite direction. That means copper will pass into the solution as the copper ionize and zinc will be get deposited in the zinc electrode. So these are the three thermodynamic conditions. When the Daniell cell or when any cell which obey these three thermodynamic conditions, then only we can call it as a irreversible cells. The first is very simple. The first is there is no change in the external EMF and also the cell, that means Daniell cell. If you give the EMF, both the external and this Daniell cell is equal to 1.1 volts. So there is a no current flow and also there is a no chemical changes. Chemical reactions takes place. The second condition, if you made a external EMF made a slightly less than to 1.1. Then there it is a current flow from the cell and the small chemical reactions is also occur. But whereas if the external EMF is made slightly greater than 1.1 volts, if you made a slightly greater than 1.1 volts, then current will flow in the opposite direction. So this is important. Opposite direction. So these are the three thermodynamic conditions. So when the cell with these three thermodynamic conditions, so then only we can call it as a reversible cell. The next one, so there is irreversible cells. Irreversible cells. Though when do you call the irreversible cells? Yes, we know that. When you call the irreversible cells means when the cell obey the thermodynamics reversibility conditions, then only we can call it as a irreversible cells. If not obey these three thermodynamic reversibility conditions, then automatically we can call it as a irreversible cells. So here is the best example for the irreversible cells. So there is zinc silver cells and also the dry cells. That means primary cells are come under the irreversible cells. How can you define the irreversible cells? Now here the cells which do not obey the conditions of the thermodynamic reversibility are called as the irreversible cells. Yes, we know that. So best example, yes, we know that the zinc silver is an example for a reversible cell, and it is represented as this one. So this is the cell representation of the zinc silver cell. So that is zinc HTSO4 and aqueous and silver. So here is the cell reaction. If you observe the cell reaction, then you can easily understand the irreversibility of these cells. For example, see here the cell reactions. So here when the zinc reaction with the acid, it will release the hydrogen gas. See this one, anode. There is no reversible reactions in between these two reactions, because here is the hydrogen gas is already escaped from the reactions. That is why we cannot reverse the reactions. So simply here also, when the silver ions absorb the two electrons and it converts as a silver solid at cathode. At cathode also there is it is not a reversible reaction. It is a irreversible reactions. So when you observe these two reactions, so we can easily understand the irreversible cell of the zinc silver cell. So here it is the zinc silver cell. How can it works? For example, if you observe this by observing that two reactions, so then we can easily understand what is the irreversible cell. See here it is when the two electrodes are connected to the zinc dissolves with the liberator of hydrogen gas. Yes, we know the first reaction in zinc case. See this one. Here it is the zinc, the liberation of hydrogen is possible and connected. So when the external EMF is slightly greater than the actual EMF of the cell, then what happens is applied to it. So the above reaction is not reversible. So because one of the product, that means hydrogen is already escaped from the reaction. So then we cannot make the reversible reactions. So such a cell which does not obey the conditions of the thermodynamic reversibility is called as irreversible cells. Yes. So these are the known as reversible and irreversible cells. The next one, so that is electromotive force. It means EMF, electromotive force. Then what is mean by electromotive force? To understand what is the electromotive force, if you observe this picture, see this one. This is a water flow. So generally, water only spontaneous flow on the way in a waterfall. See this, waterfalls. So likewise, the electrons is also spontaneously flow one way in a redox reaction. When you observe the water flow, it's the water flow spontaneous flow from up to down. So likewise here also the electrons only spontaneously flow on a way in a redox reactions from higher to lower potential energy. So if you observe this picture, you can easily understand. So this one, it is a high potential energy. That means higher potential energy. So this is a lower potential, relatively lower potential energy. So like if you observe in the cell, so see this one. This is the anode. So this is the cathode. The electrons flow from the anode to cathode. That means the high potential energy presents at the anode. So the low potential energy is present at the cathode. So that is why electrons flow from the high potential energy to low potential energy. Yes, you understand, is it? So that is a flow of the electrons. Then here, how can you define the electromotive force? So here is the potential difference between the anode and cathode. See this. The potential difference between the anode and cathode in a cell is called the electromotive force. Very simple. So what is that? Electromotive force means the potential difference. Very simply, the potential difference between the anode and cathode in a cell is called the electromotive force. So that is called as it is also called as a cell potential. It is also called as a cell potential, and it is denoted with the E cells. E cell or E naught cell. E naught cells. Then how can you write the mathematical expression for the this EMF? So here it is a expression for the EMF. E naught cell is equal to E naught reduction. So this reduction potential. So this E naught cathode minus E anode. E cathode minus E anode. Or you can write it as what are the reactions that take place at the cathode? At the cathode, it is reduction. Reduction reactions are reduction minus oxidation. Yes, you know that. Yes. So what is the EMF equation? That is the E naught cell is equal to E naught cathode minus E naught anode. So this the potential difference between the cathode and anode, it is known as electromotive force. So it is indicated with the E naught. So remember this one, this is very important. So here is one example. So if you observe the example, then you can easily understand what is the EMF. So one example, so that is calculate the EMF of the following cell. Yes, so here it is the cell representation. You can easily understand what is this. What is this cell? So here it is this is anode of reaction. So this is cathode of reaction. So zinc 2 plus. Here it is a copper 2 plus copper. So this is a salt bridge. So that is why this is the cell representation of the linear cell. This is very important. Okay. So here are some reduction potential. See this one. This is a reduction potential of the zinc and copper are given. So zinc reduction potential is minus 0.7623 volts, whereas the copper it is equal to plus 0.337 volts. So these are the reduction potentials of the zinc. So this is zinc, and this is about copper. Then what is our aim? Here is our aim to calculate the EMF of this cell. So what is the equation? EMF of the cell? E naught cell is equal to E naught cathode minus E naught anode. Yes, yes. So just you have to substitute the values of reduction potential of the anode and cathode, then you can easily get the E cell of the cell. Okay. So here the E naught cell is equal to E naught cathode minus E naught anode. That is What is the reduction potential of the here? What is the cathode? Cathode, it is a copper. Copper act as a cathode. The zinc act as a anode. So that is why the reduction potential of the cathode, it is plus 0.337 minus of minus. What is the reduction potential of anode? So that is minus 0.7623. Then on simplification, then we can get the this value, that is 1.0993 volts. So this is a E cell, the EMF of the cell. You can also write the cell reaction. So here the oxidation reactions are taking place at the anode. So what is the anode of reaction? So that is zinc plus 2. That means zinc converts as a zinc 2 plus ion after the releasing the 2 electrons. So reduction. So reduction reactions are takes place at the cathode. So here the copper will act as a cathode. So that is why copper ion will absorb these 2 electrons and converts as a copper metal. Then what is the net reaction? So here it is the 2 electron cancel. Then the net reaction is zinc plus copper ion gives rise to zinc ion plus Cu. Yes, zinc here it is converted as a zinc 2 plus, copper 2 plus, it is converted as a copper. So here it is, this is the oxidation and this is a reduction. Okay. So this way you can easily find out the E cell or EMF of any cell when you know the reduction potential value of the different type of electrodes. So this is about EMF. It is electromotive force. What is electromotive force? It is just the potential difference between the cathode and anode. This is known as a electromotive force. So the next one, the important one, the Nernst equation. See this one. Nernst equation. So what is Nernst equation? So here the word Nernst derived a mathematical relationship between the standard electrodes. This is the standard electrode potential, temperature, and concentration of the ions. The Nernst equation, it is nothing but it gives the information about the what is the relationship between present the standard electrode potential, that means EMF or not, and temperature, and also the concentration of the ions. So this relationship is known as Nernst equation. So what is Nernst equation? So remember this one, Nernst equation, it gives the information about the what is the relationship between present in between the standard electrode potential, temperature, and concentration of the ions. So this relation is known as the Nernst equation. So here is the Nernst equation. So the Nernst equation, you can write the Nernst equation for the simple reaction. So that is Mn plus n electrons gives rise to M. It is the very simple reaction. Then how can you write the Nernst equation for this simple reaction? So it is, you can write this is the Nernst equation. So there is the E cell. E cell is equal to E naught. E cell is equal to E naught minus 2.303 RT by NF log. See this one, the log concentration of the products by concentration of the reactants. See this one, concentration of products by concentration of reactants. So remember this one. I can write it as, so this is known as the Nernst equation. Nernst equation, what is the Nernst equation? The E cell is equal to E naught minus 2.303 RT by NF log. Here it is what we are writing the Nernst equation for this equation. So that is why we are writing the concentration of the M, that means products, by concentration of the reactant. So that is Mn plus. So here the E naught means, yes, we know that that's standard EMF of this cell for the 1M solution at 298 kelvins. So what is R? R means it is a gas constant. R means it's a gas constant. So what is T? Yes, T is a Kelvin temperature. And what is the N? The number of electrons involved in the cell reaction. In that means standard EMF. R means gas constant. T means Kelvin temperature. N means the number of electrons that are involved in the cell reaction. And what is the F? F means it is a Faraday of electricity. Faraday of the electricity, that is 96,500 coulombs. So it is equal to 96,500 coulombs. Then what is E? E means the electrode potential of the metal. What is the electrode potential of the metal? What is the concentration of M? That means activity of metal in the metal fuse, and it is taken as a unity. And what is the concentration of the Ml plus? So that is equal to activity of the metal ions in the solution, and it is taken into that the molarities. Now here at 298 kelvins, so this value, see this one, after substituting the all the values of the R, T and the F, see this one, after substituting the all values of these values, so that is R, T, F, then we can get the value of the 2.303 RT by F. That value is equal to the 0.059. 0.059. The equation becomes so like this. Therefore, we can write the equation so this way. E is equal to E naught minus 0.059 by N log concentration M by concentration M plus. Then we can write with the equation, and also E is equal to E naught minus 0.059 by N log concentration of products by concentration of the reactants. So this is a Nernst equation after substituting all the values of the R, T, E, F. Then we can get a simplified equation. So here it is a simplification of the equation. E is equal to E naught minus 0.059 by N log concentration product by concentration of reactants. So this is about the Nernst equation, the important one. So if you observe the example, if you see this example, determine the EMF. You see this one. Determine the EMF of the zinc electrode. See this. Zinc electrode immersed in a 0.1 M concentration zinc sulfate solution at 25 degrees Celsius. Then E reduction potential value of zinc, it is minus 0.76. Then what is the reaction? It is the upcell reaction. Zinc plus 2 electrons. See this one. Zinc electrodes immersed in a 0.1 M. See this one. This is the upcell reaction. So it is zinc 2 plus 2 electrons gives us to zinc solid. Yes. Yes. Then what is the Nernst equation? That is E cell. That means E zinc plus 2 zinc. That is equal to E naught. Zinc plus 2 by zinc minus 0.059 by N log concentration of the sorry, is see this one, this is the wrong reaction. So here it is a zinc gives rise to zinc plus 2 electrons. So this is a reaction. Okay. Yes. So this is a reaction. Sorry. So here it's a zinc oxide reaction. So that is 0.059 by N log concentration of the products. See this one. And some products are zinc 2 plus by zinc. Substitute the values or reduction potential of these that is equal to minus 0.76 minus 0.059 by N N means the number of electrons that are involving the reaction. So here it is the 2 electrons. Then what is the concentration? So here it is the concentration is already given. Here is 0.1 m zinc sulfate Cs. So that is why we are writing the concentration of here it is 0.1. Then on simplification, then we can get the value minus 0.76 minus 0.0291 and give is equal to minus 0.78955 volts. So this is a EMF of the zinc electrodes. So this way you can easily find out the EMF any electrode or cell reaction. So this is about the Nernst equation. So Nernst equation. Now here it is coming to the copper. See this one. Here is the Nernst equation for the off reaction for the copper. See this one. The copper 2 plus 2 electrons. See, this is 1 electron. Sorry, the copper 2 plus 1 electron gives us to Cu plus. The E naught is equal to plus 0.153 volts. Then substituting these values in the Nernst equation. The Nernst equation is E is equal to E naught minus 0.059 by what is the N? N means 1 electron. This is a 1 electron log. See this one. Cu2 plus. So here the concentration of these two copper 2 plus and copper plus are both 1.0. Then E naught is equal to 0.153 volts. Q is equal to 1. Q becomes 1. Q nothing but it is a ratio of the concentration of the products by concentration of the reactants. So substitute all these values. So then we can get this equation that is E equal to 0.153. That is E. What is it? Is E naught. E naught is equal to 0.153. So substitute the E naught value minus 0.059 by 1 log concentration of the Cu plus by concentration of the Cu2 plus. So both are equal to 1.0. So that is why 1 by 1. So that this whole value is equal to 0.153. So here it is another example. So these are some examples. So next one, Electromotive Series. Electromotive Series. So what is Electromotive Series? So how can you define the Electromotive Series? So here, when the metals are arranged in the order of their increasing, see this one, the increasing value of the standard reduction potential on the hydrogen scale, then the arrangement is called as a electromotive series. What is electromotive series? Is very simple. When you arrange the metals, in the order of their increasing value of the standard reduction potential, so on the hydrogen scale, then this arrangement is known as the electromotive series. Electromotive series means is nothing but it is a arrangement, a particular arrangement of the metals with respect to their reduction potential value. So can you arrange the reduction potential value of the metals in the increasing manner? If you arrange the increasing manner of the metals of the reduction potential, so then that arrangement is known as simply that arrangement is known as a electromotive force, electromotive series. So that is known as the electromotive series. See this one. So in the left side, so all metals are present. So in the right side, see this one. These are the, in the left side, all the metals, lithium, potassium, calcium, sodium, so like that. The right side, so these are the standard reduction potential of this respective metals. Then what is the electromotive series? The arrangement of metals with respect increasing arrangement, increasing order of the standard reduction potentials series. So here is a minus 3.05 volts to and 0 and plus, negative and 0 and positive. So it is a, when you go up to down, then it is a increasing order of the standard reduction potential of the these respective metals. So this arrangement is known as the electromotive series. So this is known as the electromotive series. See this. So these are the some of reactions and their inert values. That means reduction potential. So here is the lithium. So when you observe the one electron, it converts as a lithium, and it is inert value is this inert value is equal to minus 3.04. Coming to the magnesium, just so that is equal to minus 2.37. So here it is hydrogen. See this one coming to the hydrogen with the hydronium ion, H plus 2 electrons, it converts as a hydrogen gas. So the inert value is 0 hydrogen electrons. Yes, we know that this will act as it is a reference electrode. So it is a reference electrodes. So the inert value of the reference electrode, the standard hydrogen electrode, is equal to 0. Yes, we know that. So these are the negative values. So these are the positive values of the respective metals. So this arrangement is known as electromotive series. So by arranging this way, then what are the use? Is there any useful for if you arrange like this? Yes. So there are some applications of electrochemical series. So let's see some applications of the electrochemical series. So that means some uses while you are arranging these metals in a order wise. So the first one, it gives an idea regarding to the tendency of elements to lose or gain electrons. It will give the information about the which elements lose the electrons or which elements absorb the electrons. So for example, the elements with lower reduction potential have the tendency to lose electrons. It will give the electrons. So there is greater tendency to get oxidized. That means they undergo oxidize. And also they will a good reducing agents. And these are the good reducing agents. The next one, the elements which higher reduction. See this one. And the elements which are higher reduction potential have a tendency to receive electrons. So that will absorb the electrons. Higher reduction potential, the elements which are having the higher reduction potential, that will absorb the electrons. And tendency to get it reduced. And it will undergo or reduced. And they will act as a good oxidizing agents. They will act as a good oxidizing agents. And next one, that is, it will give information of the displacement of reactions. Displacement of the reaction. That means an element above in the series can displace an element below it. The element which is present above in the series. So that element, it is displaced by the element which is present below it. Yes, for example, an element with lower reduction potential. See this one, the element which will having the low reduction potential can displace an element with a higher reduction potential. It's clear. For example, if you observe this example, you can easily understand. So here it is the zinc and copper, two are there. Zinc has the lower reduction potential. Yes, we know that. And the copper having the higher reduction potential than the zinc. So hence what happened? The zinc displaces the copper from the copper sulfate solution. If you observe these reactions, see this one. In these reactions, the zinc displacement the copper which is present in the copper sulfate solution, and it becomes zinc sulfate. So that is so that is information. That information will give this electromotive series. What is that? The displacement reaction. So remember that one, an element above in the series can displace an element below it. Yes. Yes. The third one, when a cell is constructed, which electrode sits, which metal electrode will act as a anode, or which metal will act as a cathode. So that information will give this electromotive series. So based on their standard reduction potential, then we can easily say whether it will act as an anode or it will act as a cathode. So for example, the anode should be a metal higher in the series. This one, the anode should be metal higher in the series, that is present in the upside. Cathode metals lower in the series. The cathode metal which will act as a cathode, so that metal lie in the lower in the series. So for example, when a cell is constructed using the zinc and copper, see this one. In these two, zinc and copper, which will act as a anode, which will act as a cathode. So that information it will give. See here. Here it is the zinc which is the higher in the series. That means the zinc present in the higher in level. Yes. For example, if you see the series, zinc will higher in the level and copper it is below in the series. See this one. Okay. So that means the zinc which is higher in the series will be anode. That means zinc will act as an anode. And automatically copper will act as a cathode. That means copper will lie in the below the series. And also you can tell it is like lower reduction potential based on the reduction potential. The metal which will have the lower reduction potential, that will act as a anode. Lower reduction potential is lower reduction potential elements, that metals will act as anode. Yes. And higher reductions, the metals which will having the higher reduction potential, so that will act as a cathode. Yes. So this way also you can easily explain which will act as a anode, which will act as a cathode in the cell. Yes. So the next one, so that is a metal above hydrogen. See this one, the metal which is present above hydrogen in the series can displace the hydrogen gas from the daily cells. But a metal below the hydrogen, the metal which is present below the hydrogen, it cannot liberate the hydrogen gas from the acid. Yes. See, all these metals are like sodium, potassium, calcium, magnesium. These all metals present above the hydrogen in the series. Present above the hydrogen in the series. So that is why. So they can displace within. That means they can give the hydrogen. They can liberate the hydrogen from its acids. So if you observe these reactions, sodium in reaction with the hydrogen sulfate, it liberates the hydrogen gases. Potassium, it is also liberates the hydrogen gas. Calcium, it is also liberate the hydrogen gas. Magnesium also will with the liberation. Yes, liberation of gas. That means the metals which are present above the hydrogen, so that will liberate the hydrogen. So remember this one. So with the metals which are present below the hydrogen in the series, that will not liberate the hydrogen gas from its acid. So remember these ones. So these are some applications of electromotive series. So by using the electromotive series, then we can say whether it will act as a anode, cathode, and which metals will give the liberate the hydrogen gas from its acids, and also a displacement. It will also give the information about the displacement reactions, and also it will give the information about the which metals will give the electrons, or which elements will absorb the electrons. So these are the some applications of the electromotive series. So electromotive series is the most important one. So here is the electromotive force. So it is the important one, and its applications. And Nernst equation, that is important one. And electromotive force, it is also important one. And reversible and irreversible cells. So these are the important topics they will ask in your examination. So these are some important questions.